In this lecture, we're going to provide an introduction to statistics by first examining the general role of statistics in the research process. And one way to describe that is through this idea of the research trinity, suggesting that there are three core elements to conducting research, which is design, measurement, and analysis. And in the first part, when we think about conducting research, the design aspect is really the first stage that establishes what I call the integrity of the research. For a research project to be carried out, it really needs to begin with the process of designing how to answer a particular research question. And the overall design of an experiment will establish what's called the internal and external validity of that research. In other words, can we place trust and belief in the outcome of the experiment? If we want that to happen, that's going to be based upon a sound design for that study. Now, once we have a design set up, we can then move on to the measurement phase, where we actually begin the process of obtaining information. But before we do that, all contained within the measurement phase is that we have to determine and define what are called constructs, the ideas that form the foundation of our research question. And once that's carried out, we can set up what are called operational definitions, which are very precise, very specific definitions for the different elements in the research question. And when we conduct our information gathering, that we often refer to as data, applying measurements that are reliable, in other words, measurements that we can count on producing consistent results time and time again, is going to be a necessary component of that measurement arm of the research trinity. The third step here is the analysis, and the analysis establishes what's often referred to as conclusion validity, where we can place some trust in the final statement of the research to be tied back to the measurement and the overall design of the study. And the analysis aspect is where we evaluate the information that was gathered. And we do that by evaluating hypotheses, both research hypotheses and statistical hypotheses that were stated as part of the design aspect of the study. Another way to examine the research process is a little bit more specific here, a little bit more tangible in these four critical steps that you see that moves progressively from the left to the right. And the first part begins with the collection of data. Now, this assumes that we've moved past the design aspect as outlined on slide number 2. But when we talk about collecting data, we're gathering information. And that information could be quantitative in nature or qualitative in nature. When we collect quantitative information, we're applying numerical values to our observations. Once we've collected the data, we then move on to the next phase, which is where we analyze the data. And from a quantitative perspective, we apply statistical procedures. And these are well-established use of formulas, equations. We use graphing techniques to analyze those data as well. And when I use the term data, I'm generally referring to information, but in a quantitative approach, that information takes the form of numerical values. Now, the analysis of data is the relatively easy part because it's prescribed by the equations, by the formulas, and by the graphs. The challenging part of the research process is to interpret the data after it's been analyzed. And that's where we relate the results back to the original research question and any hypotheses that have been stated. And then once we've made the data interpretation phase complete, we're then able to present findings using a wide range of various media. And that includes publishing results as a peer-reviewed paper, presenting the results in some form of conference environment, or publishing it as a report. Specifically, when we talk about analyzing data, quantifiable data, we take a look at this flow chart here at the bottom, where we begin with the idea of making a conclusive statement about a population. But we know that it's extremely difficult to measure every element of a particular population, but this is where our interest starts. So the next step here is to obtain a sample from the population of interest. Now, ideally, we can take that sample in a random manner, but if we're measuring items from people, there are ethical issues that don't always lend themselves to a true random selection. But regardless, once we have a sample that is accessible, that we can evaluate, we then apply numerical values to the information that we obtain, and we compute what are called sample statistics. And the X symbol with a bar on top is the standard symbol for the sample mean, and we'll get into that repeatedly here in this video and in subsequent videos. Now, once we calculate a range of different statistics, the sample mean is just one descriptive statistic we can generate. We then use that in an inferential manner. In other words, we then infer the results from our sample back to the population. And you notice that a measure of the population mean, or the population average, uses Greek symbols, whereas when we calculate statistics directly from a sample, we use English symbols. So when we talk about statistics, statistics is just simply defined as a body of methods for obtaining and analyzing data, and it's made up of formulas and equations and prescribed methods that we'll get into throughout through a number of these lecture videos. The first step when we calculate statistics is to compute what are called descriptive statistics. And descriptive statistics are those numerical values that summarize information in a collection of data. So if we obtain information from our sample and we apply numerical values to each person in this example, then we would take the values obtained from each person and we would compute something like an average of those individuals, and those would just be used to describe the sample. But in inferential statistics, what we want to do once we've computed the statistics of the sample is we want to have a set of methods that allow us to infer to the population, and those methods are important because from a research perspective, we rarely, if ever, have access to the full population, but we're able to access a much smaller subset of the population in a sample. And that inferential procedure, where we have our directly observed statistics and make inferences back to the population, gives rise to the probability of outcomes. And so what we eventually want to be able to conclude is whether there's a greater probability of an occurrence of our observations than just by simple random chance. And that's something that we'll certainly get into much later. So to examine the difference between a population and a sample, we simply define the population as the total number of cases or items of interest within a defined region. Now, a population can be more specific. Some examples include all university students in Canada. We may be interested in all Canadians over the age of 65, or we may narrow our population of interest with a research study and just zero in on all Canadians suffering from arthritis. Perhaps our population of interest are all people with cardiovascular disease. And so if we wish to summarize the information that is quantifiable from a population, we would generate what are called population parameters. And those are numerical values that characterize the population. When we talk about population parameters, we use Greek symbols to represent those descriptive values that we generate from the population. So Greek letter mu here is the standard symbol for the population mean or average. Sigma, lowercase Greek letter sigma, is the symbol that is used for the population standard deviation. This symbol here is Greek letter rho, and that is the symbol used to indicate the population correlation coefficient. So we'll get into these in much greater detail in subsequent videos, but just note here the main point is that when we talk about population parameters, we use Greek symbols to represent various calculated values. Now that's different than a sample. So when we take a look at an example here, and we ask the question, how many university students are there in Canada? We take a look at the population here. So with my research question, the population of interest would be all university students in Canada. And in 2023, it's been estimated that there's just shy of 1.5 million university students in Canada, and this numerical value is sourced from a range of different organizations. Now, if I wish to carry out a study examining university students, it would be extremely difficult to gather information from all students. So what I might do is obtain a sample of only 50 undergraduate students drawn from the population. And when we deal with small samples, the underlying question that is often asked that we as researchers we always need to be aware of is our sample representative of that population. Now statistics will not fix this if it's not. To make our sample representative, this is all based on research design. And remember, statistics is something that's carried out after that fact. So once we have our 50 undergraduate students, we can then take measures from those 50 undergraduate students and compute statistics. And so as we saw on slide number 5, where we can generate numerical values for the population that we call a population parameter, we have sample statistics in a similar sort of way. And the sample statistics uses English letter symbols. And these are just 3 examples. We have X with a bar on top, and we would just refer to this as X bar. We have lowercase s. Sometimes you see the subscript X, sometimes you don't. I'll be using that interchangeably throughout these videos. And we have the symbol R. So these 3 symbols are those that capture the sample statistics in the similar way that we saw on slide number 5 with the population parameters. So this ends the first part of our introductory unit on statistics.